I want to just introduce the plenary speaker, Professor Gordon Wetzstein, Assistant Professor of Electrical Engineering and by courtesy of Computer Science at Stanford University. He is the leader of the Stanford Computational Imaging Lab, an interdisciplinary research lab focused on advanced imaging, microscopy, and display systems. At the intersection of computer graphics, machine vision, optics, scientific computing, and perception, Professor Wetzstein's research has a wide range of applications in the next-generation computer electronics, scientific imaging, human-computer interaction, remote sensing, and many other areas. Prior to joining Stanford in 2014, he was a research scientist in the Camera Culture Group at the MIT Media Labs. He organized the IEEE 2012 and 13 international workshops on computational cameras and displays, as well as the upcoming 2017 International Conference on Computational Photography at Stanford, which is in May, by the way, May 12th to 13th. And today he's going to tell us about how he's making virtual reality better than reality. Please welcome Professor Wetzstein.
Thank you so much for the kind introduction, Nitin, and it's a true honor to be here. Today, I'd like to talk about the state-of-the-art of virtual and augmented reality and where I think this field is going to be going. I'll tell you a little bit about the technological developments that we've been doing in our lab, and I'd like to ask the question whether it's possible to create a virtual reality that for some people in some applications may even be better than reality. So I'll get back to that question later in the talk. Next-generation computing platforms are widely believed to be portable and offer a seamless interface between the physical world and the digital world. Phones today are already portable. We carry them around in our pockets and we can interact with them. But the interaction is confined to the actual display, which is a small device. So in the near future, I envision this to be seamlessly integrated over our entire visual field and provide this seamless interaction between physical and digital. So that's something we envision. A key technology to make this really happen is a near-eye display. The near-eye display is the primary interface between the user and the digital world as well. So we need to understand human perception, especially depth perception, as well as the optics and the computation that's required to generate new kinds of experiences. Today's AR and VR displays look somewhat clumsy, they're a little bit bulky, and maybe not the kind of thing that we would like to wear on the street. But if we've learned one thing over the last 50 years in Silicon Valley, then it's that computing platforms that cover an entire room or a building can, within a decade or two, shrink to the size of something that you can carry around in your pocket. Just keep in mind that the phone that you carry around today is about 1,000 times faster than the computer in the Apollo 11 mission. So that's what propelled mankind to the moon. And we carry it in our pocket right now with 1,000 times as much compute power. So we can only envision what these AR, VR systems look like in the near future. And you can think about wearable computing as a natural extension of this technology trajectory from personal computer to laptop to phone. But in fact, people have been looking at these technologies for a long time. And everybody who talks about history of virtual reality will probably show you a different history. I'm going to start in the 1830s, where people like Charles Wetzstein and others invented the stereoscope. These are devices that allow you to see a stereoscopic 3D image. And people in these Victorian times would gather and look at photographs and enjoy these as entertainment. You can actually go to the Library of the Congress and find a huge collection of stereoscopic photographs from the American Civil War and Lincoln, for example. So these kinds of technologies have been around for a long time. In my perception, in the late 60s, Ivan Sutherland and others made significant progress in making these technologies digital. So Ivan Sutherland built a system that he called the Sword of Damocles, which already included most of the components that we now have in the Oculus Rift, the Vive, and so on. It was actually an optical see-through augmented reality system with mechanical tracking, CRT monitors. It created the need to compute images that were indistinguishable from the real world. So that's the big challenge for computer graphics, even today. the need for computer graphics was created by designing technologies that we now think are really new and that have been coming up over the last few years. So the first consumer product actually came out in the mid-90s already by Nintendo, the Virtual Boy. It sold about 750,000 units in Japan and the US. I don't know if you've had a chance to see any of these yet. I just bought one from eBay, for example. It's very simple, only line graphics, no occlusions, no shading or lighting in there. But the core technology is still basically what we had in the 1830s. So now over the last 5 years, we've been seeing a lot of commercial interest revived in especially VR displays, and we think about them as gaming platforms. But I'd like to think about them as a new computing platform and something that we can leverage to give us entirely new experiences. So the question then is, if we want to have these new experiences, what does it take to get there? And we can call it VR 2.0 or whatever you want to call it. What do these technologies have to offer in terms of visual experience and experience overall to give us a satisfying experience? Sorry. So if we look at what's in this technology today, we mainly see commodity hardware. It's pieces of plastic, 2 lenses, and cell phone components. So in my opinion, the cell phone industry has really been driving the technology that is now also enabled AR and VR. High-resolution, small-scale screens, LCDs and OLEDs, are really what's driving the visual experience, and low-latency tracking is enabled by low-cost IMUs, inertial measurement units, that we're using in phones also to flip the screen when we turn our phone. So these enable orientation tracking in the VR and AR experiences. There are a couple of other components in here, but most of them are head straps and injection molded plastic parts. So the basic operation principle of VR and AR displays today is very similar to what we've had more than 150 years ago already. We look at 2 stereoscopic images that fuse together by our brain and give us this experience. We've replaced the photographs by our phones or digital screens that can update content dynamically, and we can do orientation tracking. That's the major difference. The rest is almost the same. If we look at the optical principle of operation of head-mounted displays today, they're all based on what's known as the magnifier principle. So in this case, we're going to have a phone or a small screen very close to the eye. In fact, so close that we couldn't focus on the screen. It's only a few centimeters in front of your screen. You cannot focus your eyes on that screen. That's the reason why we use magnifying lenses. The magnifying lenses will create a virtual image at some distance that is enlarged, but it also appears farther away. So your eyes can actually focus on that image, and you get a natural view of that plane. The optics are actually very simple and governed by the Gaussian thin lens formula. The distance between the microdisplay and the lens and the focal length of the lens completely define where that virtual image will appear, at least to first-order approximation. And so now we're looking at 2 different planes floating in space. And the question is that a natural view of a digital world? Is that what we perceive in the real world? It's not. And it has a lot of limitations. But before we go to the limitations, let's try to understand human depth perception, at least the parts that are related to stereoscopic displays, and especially near-eye displays. So there are many different depth cues that the human brain uses to perceive 3D-ness or depth of a scene. The ones that are most important for these types of displays can be categorized into binocular cues and monocular cues, and also into oculomotor cues and visual cues. For example, vergence is an oculomotor cue. The extraocular muscles in our eyes will rotate our eyeballs in their sockets. If I look at something really far away, my eyeballs are going to rotate outwards, and they're almost parallel. If I look at something very close, they're going to rotate inwards, and the muscle state will be sent as a signal to the brain that's being interpreted as what the distance of an object is. The vergence cue is driven by binocular disparity. So binocular disparity is a visual cue. It comes from the fact that we perceive 2 different images, 2 different perspectives of the scene on our retina. And because the the resolution on the retina is very dependent on the location. The fovea has the highest resolution. The eyes will going to verge so as to keep the fixated object at the highest possible resolution. Right? So we're going to shift the images around on the retina to get the best possible experience. So now on the monocular side, even if you only had a single eye, there are a lot of depth cues in there. Accommodation is the oculomotor cue. These are ciliary muscles connected to the crystalline lens in your eye that can deform its shape, and the shape itself defines which distance is going to be conjugate to your retina, and you will perceive that in focus. Other objects that are farther away from that focal plane will be out of focus. So that's very similar to the depth of field effect that you may know from a camera. But the retinal blur will drive the accommodation in this case, and both are together with the binocular cues create a set of cues that the brain uses. These are also interlinked. Now it's easy to create binocular disparity cues with a stereoscopic display or a head-mounted display. You simply render two different images that are rendered from the correct perspective, and your brain will automatically verge. Problem is that the accommodation cue, the retinal blur cue, is very, very difficult to generate, and that creates a lot of shortcomings. So in the real world, all these cues are matched. The brain uses consistent input from all the sensors. If we verge at an object, we will also focus at that object, and depending on what we're looking at, the vergence and the focus will basically just be driven to the fixated object. In a VR display, or any stereoscopic display, the vergence and focus cues are decoupled artificially. So any object you're going to be looking at, your eyes will follow the disparity cues because they're rendered that way. That's easy. You can drive the vergence to arbitrary distances using computer graphics. But you always have to focus on that one plane. And the reason for that is if you wouldn't focus on the screen, you wouldn't see a sharp image. It would just be blurry. So your eyes naturally accommodate to that plane, and they verge to a different plane. And that's a big problem for people with normal vision, because now cues that are neurally coupled in the brain are artificially decoupled. And what happens in these cases is that from an evolutionary point of view, if cues don't match, people get sick. That's the same for motion sickness, where we get one input from the vestibular system that tells us how we're moving, what the gravity is, and we get a different signal from the visual system. If these cues don't match, the body thinks that we're poisoned, potentially, and reacts accordingly. So as I said, this vergence accommodation mismatch is a big problem for people with normal vision. So how many of us actually have normal vision? Very few. A few. Okay. So let's take a look at some numbers. This is all US population. So myopia is nearsightedness. More than 40% of the US population are nearsighted. About 25% of the US population are farsighted or hyperopic. And let's face it, all of us are getting older, and after a certain age, which is usually about 40, 45, we're gonna get presbyopic, right? If you don't recall what that means, let me try to illustrate that. So normal vision would allow you to accommodate over a wide range, from infinity to somewhere very close by, about 20, 25 centimeters in front of your eye. You can test it yourself if you just hold up your hand and see how close you can move your hand until you see a blurry image. Nearsighted simply means that that range of accommodation is shifted closer towards you. So you can't really accommodate very far anymore, and you need vision correction to allow you to see far. Hyperopia is shifted the other way, so you need correction for near vision. And presbyopia is the fact that the crystalline lens in the eye will get stiffer with time, and it's more and more difficult to actually deform its shape. So our accommodation range will become smaller and smaller, to the point where you can only accommodate at one plane. And that's in the real world. So for the next couple of minutes, I'd like to talk about some computational near-eye display technologies that can address these issues. And the point I'm trying to make is that different people, different users with different refractive errors will need different ways to create an optimal experience for them. So the questions I'd like to ask is, first, can computational displays replace eyeglasses in VR AR? These devices get smaller and smaller. It's becoming more and more difficult to wear vision correction together with near-eye displays. So that's something that we'd like to talk about. The second question is, how do we address the vergence accommodation conflict differently for users of different ages, because it turns out that people with different ages require different modalities for the optics to work. And then third, we're going to talk about some technologies and see how effective they are in addressing all of these questions. And the technologies that we'll mention is gaze contingent focus, monovision, multiplane displays, and light field displays. So these are all a range of different technologies that have been introduced over the last 5-10 years to address focus cues in VR/AR. So let's start with the first question. Can computational displays effectively replace glasses or vision correction in VR/AR? Well, it's not possible with the current design. The current design uses this fixed focal length of a lens, fixed distance between micro display and the lens, and it creates this magnified virtual image at some fixed distance. If you can focus on that distance, that's great. If you can't, you're going to see a blurry image. So adaptive focus is an idea that's been around for a little while, and that's something that can be very useful, and we're going to use that as a platform to try to answer these questions. Adaptive focus can be implemented in two ways. Either you move the physical microdisplay inside the head mount while leaving the lens fixed, so you're altering the distance between microdisplay and lens, and only a couple of millimeters of movement there will create a huge amount of motion of the virtual image in the scene. The second idea would be to using focus-tunable optics. These could be liquid lenses that you can program that deform their shape, very similar to the crystalline lens in the eye. They could be reflective mirrors that can be deformed. In this case, we're varying the focal length of the optics and achieve the same effect. We can program the distance of the magnified image. So these are not new ideas. In fact, if you go back to the original patents from Sensorama in 1962, they already had adjustable, manually adjustable focus, right? So then, so what I've also found, and I hope I didn't forget anything, was Henry Fuchs had a paper in 1984 where they hacked loudspeakers from a stereo and used a deformable membrane on top of them to basically program them. And over the last couple of years, people have been looking at using focus-tunable lenses and mirrors to drive accommodation. And so here's our take on a focus-tunable display. Most people are working on making VR displays smaller. We probably built the world's biggest VR display in the lab. The reason for that is that we want to present stereoscopic stimuli at a very high visual quality and then also measure the accommodative response of human vision. So what you see here are two high-resolution LCD displays on the side. We have these relay optics that create an intermediate image. We have these focus-tunable lenses that can change the focal length in about 15 milliseconds. So at 60 hertz, basically, you can freely program where that virtual image is going to appear. There are beam splitters that will direct the light into your eyes. What we notice is very important is to account for the interpupillary distance between different users. Everybody is going to have a slightly different distance. People usually talk about 6.4 centimeters or something in that order. But people are very different. If you don't get that right, it may degrade the experience. And so we put one of these arms on a translation stage that we can program before the user uses it. The most important piece of this equipment is the autorefractor. This is a device that's used in the optometrist's office, and it'll look with near-IR illumination into your eye and measure where you're accommodated, where your eyes are focused at any given point in time. So we can use this device to show a stereoscopic stimulus and then measure what the response is. Here's a view from the person's perspective, looking into the display. You can see these two different images. And we have these relay optics that basically create an intermediate image inside the optical arm. We use photographic lenses because they just give us the best image quality over a wide range of the spectrum. And then we have these focus-tunable lenses in the arm that can change the location of the intermediate image there. And that allows us to change the point spread function of the display. So you can see what a user would see as they were accommodating at different distances. If you accommodated exactly where that virtual image is, you're going to see a small point for every pixel. As you accommodate somewhere else, you're going to see a blurred point. So we can change that. Last summer at SIGGRAPH, we brought the entire display to Los Angeles, and we showed it to a couple hundred people. We showed them cool demos, but we also ran a user study in disguise, with their consent, of course. We had a device that's called the Ein Netra That's a portable device that allows us to measure people's prescription. So everybody's going to look into this device and manually adjust it until we know their prescription. And then they look into our display, and we do a couple of tests with them. So here are the participant statistics. We had more than 150 people in this test, age range 21 to 65. We believe this is the largest study on VR optics that we have seen, at least, that's published. You can see in light blue the people with normal vision, so that's actually a very small fraction of everybody we tested. People in purple are presbyopes, and everybody else has either hyperopia or myopia. So this is self-reported, right? So we actually measured their prescription, but here we just showed whatever they thought they had. Most people didn't even know what myopia, hyperopia, presbyopia is, which is fine. So one thing we found is that refraction in different eyes is usually different, or oftentimes. You don't necessarily need the same prescription for each eye. And most people are also myopic, versus only a few people who are hyperopic. So these are the participants of our study. And we had about 70 people in this case who need vision correction. The first task we had them do is look at a target, a stereoscopic target, at multiple different depths. And then we asked them to rank how blurry the target is or how sharp. That's a relative measure. And then we also asked them if they could fuse the image. So one big limitation of these focus cues is if you violate these cues too much is that it's not just that the images get blurrier or sharper, it's also that you can't fuse the stereo pair anymore, right? So if the divergence accommodation conflict kicks in, we expect that people can't fuse these images. So here's what we found. On the x-axis, you can see different distances for these targets, ranging from 1 diopter to 4 diopters. So on the right, we get closer to the viewer. And on the y-axis, you can see relative sharpness. This is what we got for not dialing in people's prescription, and this is what we got when we dialed in people's prescription. So it's not really surprising that by measuring their prescription and accounting for that in the display optics, they will see a sharper image. I mean, that's the whole point of doing vision correction. But we also had people with contact lenses and normal vision rate these measurements, and basically what we show is that you can get the same experience of vision correction with glasses in the optics of a near-eye display. So that's great. So next we tested the fusion. How likely are they to fuse the images, or do they see double vision sometimes? And in this case, we have a slight improvement of the correction over the uncorrected version, which basically means that seeing a blurry image doesn't necessarily mean that you can't fuse the images. It's still possible to get a stereo fusion, but you get slight improvements for that. Okay, so the summary is you want to be able to dial in people's prescription into a head-mounted display. If you want to give them a really good sense for the digital world that you present to them, but of course also for the real world. So next, we use the same device and the same participants to see how we can best address the divergence accommodation conflict for users of different ages, right? So here's again the conventional display mode where we have a virtual image, this magnified image of the optics at some fixed distance, and we render a stereoscopic image at a different distance, either closer or farther away. So the divergence will follow the stereoscopic target. The accommodation will be fixed on that plane. It's been shown in many previous studies that divergence accommodation conflict creates eye strain, makes you tired, it improves depth judgment performance, and there are many other nauseating consequences of this. So with this adaptive focus display, we can actually make sure that all these cues are consistent with one another, because we're driving the focus of the display, of the magnified display, to wherever the stereoscopic target is being rendered. And right now, we're just rendering one target, not a complex scene. So in this case, we have a target that moves in and out continuously of the scene over the range of about 4 diopters, or 3.5 diopters in this case. And we ask people to just look at the target and try to follow it naturally. And here's what we get. On the x-axis, you can see time, about 20 seconds here. And on the y-axis, you can see what distance the stereoscopic target is being rendered at. So the distance here is measured in diopters. So this is a range from that I just showed you from about infinity to something pretty close, right? A range of 3.5 diopters. The stimulus moves in and out sinusoidally. So ideally, we'd like to see the eyes exactly following the stimulus. Tested 59 people with corrected vision and found the individual responses to be in gray and the average response to be what you see in orange. So actually, they follow the stereoscopic target a little bit, right? There's a little bit of a gain for the conventional display mode. What we expected to see is that they basically don't leave that one plane and basically get a zero gain. But due to the fact that all these cues are cross-coupled in the brain, there's going to be some disparity-driven accommodative response, and that's exactly what we're seeing here. So there's a non-negligible cross-correlation between vergence accommodation. So next we tested the dynamic stimulus. Again, we have the stereoscopically rendered stimulus, and here's what we get for the dynamic mode. In this case, we have 24 people, and we get a much more natural gain. The gain is almost what we expect to see from the stimulus. Again, it's not surprising, but the idea is to drive people's accommodation with the display itself. The display only has a single plane. We need to guide the users in their accommodation if we want to create visually comfortable experiences. And that's a statistically significant impact here. So for presbyopic people, I mentioned this earlier already, the accommodation range will shrink over time, which also means that as we get older, the closest distance to which we can accommodate is going to go farther and farther away. You can see this here. This is from a paper in 1912, so this is well known. Over the age of 45 or so, it's going to be confined to something really far away. The most widely used vision correcting technique is known as bifocal glasses. You look up, you can see far. You look down, you see close. So depending on where you're looking at, you're going to get different prescription. So now we ask the question whether this dynamic mode is equally helpful for people with normal vision and with presbyopia. So I'm going to give you a dynamic gain. So how much did people follow the stereoscopic target in depth, moving in and out, with age? And what we see is that as they get older, they don't follow the target as much anymore. And that's also to be expected because they're basically presbyopic. If we use the dynamic mode, we see the same trend. We can drive people's accommodation when they're young, when they have corrected vision, and under a certain age. But for older people, there's nothing you can do. In fact, I'll show you in a second that when you try to drive people's accommodation who are presbyopic, you're going to show them a blurry image, basically, and you degrade their experience. So here's a plot that we found from the literature where people measured people's responses, accommodative responses for physical stimuli. So we see almost the same trend for this dynamic condition. So again, using this dynamic condition, adaptive focus, we can create something that is very similar to the natural world. So let's look at age-dependent fusion. When we ask people under the age of 45 to see if they can fuse the target at very close distances, so this is closer, the target is closer to you, we see a significant improvement in fusibility when we use this dynamic effect. And as people get older, there's a lot of noise in the data. There's a lot of personal variance, and it's not quite as clear. It still seems to improve the condition, but the error bars are pretty high still. So when we look at age-dependent sharpness, what we'd expect is that younger people, they can freely accommodate. Anywhere you show them a target, they'll just accommodate there, and they'll see that. And that's exactly what we see in the data as well. But for older people, as soon as we try to drive their accommodation, we're moving the target outside of their accommodation range, and they're going to see a blurry image, right? So the summary is this: for young people, you want to drive their accommodation. For older people, you don't. Because if you do the opposite, you're going to create a worse experience than conventional displays. So now let's look at what effective technologies are to address this. Because now we know what experience we'd like different people to have, but we don't know exactly how we're going to give it to them. So if you put this adaptive focus mode into a display, you definitely need eye tracking. So we did a preference study first, where we just showed people complex scenes and drove their accommodation depending on the center of the display. As soon as they look around, you're going to emphasize the vergence accommodation conflict, and people get headaches right away. So you need eye tracking, and you need to know exactly what the person is looking at and drive their accommodation to exactly the object that they're fixating at. So we built prototype that uses a stepper motor mounted on a Gear VR. We connected that to the manual focus adjustment wheel here, and we used an eye tracker in the display. So these eye tracking cameras work in near IR, so you don't know that they're there. They're very small, but we know exactly what you're looking at. And then we can use the motor to drive the distance between the phone and the lenses at a very fast rate. So we can drive it in basically the virtual image over 3 diopters in about 250 milliseconds. That's slightly faster than the response time of human accommodation. And so that's a really reasonable rate. I mean, you wouldn't build that in a consumer product, but it allowed us to do some studies. So here's a camera looking into the display, and the little red circle shows you where the user is accommodating, basically. So right now, the user is accommodating on the right. Now the user is accommodating on the left, and the display will immediately follow and move the virtual image plane farther away. So we are now using a camera and manually pulling the focus to show you what the eye would do naturally. It would just follow that stimulus, right? So the user looks to the right. The virtual images move closer. Because the camera is at a fixed focus, we have to manually move it forward. And that gives you the natural signal. I'm happy to discuss this later if this is confusing. But basically, we see exactly the effect that we'd like. So we showed the first version of this prototype also at SIGGRAPH last year, and got a really nice reaction from people. We did a follow-up user study at Stanford where we did a preference study. We showed people this display with a couple of different display modes, the gaze contingent focus and the conventional mode. And what we saw is that for scenes that actually have objects very far and very close at the same time, we see a significant improvement in preference. People like the gaze contingent focus much better. If you have a scene where, like this one, where all the objects are really far away, you don't see an improvement, right? So these focus cues are very important for objects close by. But if you have objects mostly at a distance or only close by, you just put the focal plane there, and you're fine. Another technology that we've been investigating over the last 2 years, and there was also a study in Marty Banks' lab, was analyzing monovision. So monovision is an idea where you put each eye at a different focal plane. So it sounds terribly uncomfortable, but it's actually not too bad. The idea was that people who can still accommodate, so young people, we could drive their accommodation to one plane or the other, and the dominant eye that would actually drive accommodation would switch. For this prototype, we actually built the focus tunable lenses into a very small form factor, and then later also used the benchtop prototype to measure accommodative response. So we did not see a statistically significant effect of this method. And in fact, many people found it comfortable, but some people found it very uncomfortable to get their accommodation set to 2 different distances. Multiplane VR displays is yet another technology that people have been talking about for the last 15 years. The idea was originally introduced by Yannick Roland at University of Rochester, and then extensively evaluated by Marty Banks and others. So this is a really interesting technique. The big problem with multiplane displays is that you need to scan out the entire volume in front of your eye, and that requires really high-speed displays. So flicker can be a huge issue in these cases. About a year and a half ago, we presented an alternative technique that also used 2 layers, but our goal was to emit the light field into the eye. Many people talk about light field displays or near-eye light field displays. I'd just like to use this opportunity to clarify what I understand a light field display is. We implemented it with 2 LCD panels that are spaced at a couple millimeters apart. So they're virtual images. The magnified images are actually about 1.5 meters apart. And they just use a single backlight. But the goal for a light field display would be to emit all these different rays, which comprise the light field, into your pupil. So when you think about a stereoscopic display, you usually think about you project one image into one eye, different image in the other eye. What we'd like to do here is we actually want to project many different images into different parts of the pupil of the observer. So we're going to have a multi-view display for each eye, right? So we're going to shine one image in there, one image in there, one image in there, and so on. That would represent what we would see in reality. And that's the light field. The light field is a collection of images showing the same 3D scene from slightly different perspectives. And in fact, they may all look the same to you because the change in viewpoint is so small. But that change in viewpoint, that parallax over the pupil, is the key to driving the focus. Right, so here we see one image should be going into one part of the pupil, other image should go into the other parts of the pupil. And we developed a non-convex optimization framework that's based on earlier work that we did at MIT on the tensor display, uses non-negative tensor factorization implemented in real time on the GPU, so pretty heavy math, to find a good approximation of this light field. And that's what I understand as a light field display. So now we don't need eye tracking, we don't need focus tunable optics, we basically generate all the light rays entering your pupil. And on the left, again, you can see a traditional head-mounted display. When you focus the camera or the eye on the plane, you'll see a sharp image, and when you don't, then you see a completely blurry image. On the right, you see the light field, and in this case, we didn't change anything in the display. We just pulled the focus of the camera, and you can see this depth of field effect, right? That would drive your eye naturally at to different distances. Again, this is very important for all objects that are close by. So anything you can touch, anything in this personal interaction space. The idea itself was built on something that we had worked on before, which we call the vision correcting display. In this case, we actually used a very simple parallax barrier, which is just a transparency with a couple of holes in it. We mounted that on an iPod Touch, generated a light field inside, and then project a light field into a person's eye. What you can see is that, in this case, the camera is completely out of focus. It's not focused on the display at all. You can't even read the text or see the buttons, but if we pre-compute the light field and observe it through this parallax barrier, if we have a high enough angular resolution, we can create these focus cues and create the illusion of a sharp image being emitted outside of the physical device. So this is not a volumetric display. It shows you a digital image outside the physical device. And this is really enabled by high-resolution panels that we have at our disposal right now. I should mention that the biggest limitation of all these multi-layered light field displays is diffraction. So as soon as if you think about light as rays, as soon as you have a ray of light going to the first panel, it's going to be blurred on the rear panel. And the smaller the pixels get, the more blur you will have on the rear. And that's mostly because each pixel acts as a small aperture in all these multi-layered light field displays. In 2004, we actually built a projector implementation of this idea already using LCOS. They have a very high fill factor, and this diffraction issue was not the case in this particular display. So the less spacing you have between pixels, the more you can disguise the diffraction artifacts. So let me give you a summary of what I've been talking about so far. So focus cues in VR AR are very challenging, but very important. Adaptive focus can allow you to correct for refractive errors, such as myopia or hyperopia. But if you want to do that right in a consumer product, you need eye tracking. So gaze contingent focus is the right way of implementing this mode, but only for young people. For older people, you just want to show them a fixed focal plane at the right distance. Multi-layer displays can require high-speed modulation, and monovision hasn't shown any improvements so far. So the light field display may be the ultimate display, but there's a couple of engineering problems that we still need to solve. So in the near future, in the next year or two, I think this gaze contingent focus idea is ready to move into consumer products, and we're working with a couple of companies in doing that. So can we make a virtual reality experience better than reality? Well, we can for some people, especially for presbyopes who cannot accommodate at all distances. So in the real world, they need vision correction. In VR, we can show them a plane that is perfectly corrected for their range of accommodation, and in some applications may create a digital content that is better than what they see in the real world. VR and AR is really a frontier of engineering right now. I've only talked about focus cues and visual accessibility of these devices, but the vestibular visual conflict, creating motion sickness, consistent occlusions in AR, form factor, building waveguides and so on. These are big challenges that we need to solve to get to this vision of using AR as a seamless interface. I would like to briefly touch upon another topic, which is not just building technology for the sake of building technology, but actually delivering experiences. So that should be the goal for all of us. So this is my friends and I last summer at a vacation in Italy. We like to do mountaineering, climb on mountains, but my family can't really share this experience. So I would like to have technology to be able to capture these kinds of moments and then share them with people. And VR and AR could be one technology to do that. It allows you to travel to distant places where you can normally not go. The problem with conventional panoramic cameras or stereoscopic cameras is that they can't really reproduce, stereoscopic vision over the full orientation of the head. So a lot of consumer electronics companies have come up with this idea of using camera rigs that look outside, basically capturing a 3D slice of the light field, and then you can reproduce this cinematic virtual reality content. The standard format for this kind of content is omnidirectional stereo right now. That's a multi-perspective projection. That's basically 2 slit cameras rotating on a line. This is used by Google VR, by YouTube, and Facebook as well. The big challenge for this technology is that you capture a lot of data. All these cameras record in the Facebook 360, 17 gigabits of data per second. You need to compute optical flow between all these cameras, and then do view interpolation, which often fails and is super power hungry and computationally intense. Facebook 360, tomorrow's plenary talk, requires 17 gigabits of data per second. It has a fiber link to a SSD RAID, and it requires hours, days, or even weeks of compute time, right? So you need a dedicated data center, basically, to process this kind of data. So we've been interested in capturing data as well as displaying it. And one idea that we came up with recently is using spinning line sensors, basically, to capture this omnidirectional stereo format directly into the camera. So we don't capture more pixels than we need and throw them away. We just capture directly this omnidirectional stereo content. So this camera uses 2 really fast line sensors behind fisheye lenses, and these are mounted on a rotating platform with the slip ring connected to the stationary electronics. So I'll just show you some results and then wrapping up. So here's one scene that we captured at 5 frames per second in 4K resolution, so 4,000 pixels vertically, 8,000 horizontally. This is one of my students. Right now we are playing the video. So really just 5 frames per second, but it gives you a really good sense of immersion. You can see the seam in this cylinder that we use for safety. Actually, there's one seam in the acrylic. But basically, we can stream data live from spinning line sensors capturing omnidirectional stereo panoramas. So in conclusion, to advance AR/VR technology, we don't just require engineering. We need to understand human perception, optics, signal processing, and computation. Developing technology alone is not enough. We actually need to think about the experience that people want. That's something that we're also teaching our students. I developed a course on virtual reality, EE 267. That's a course on build your own head-mounted display, where the students learn everything about graphics, stereo rendering. They put the head-mounted display together from scratch, implement the sensor fusion of the IMU on an Arduino, and then build really cool projects. But I'd like to leave you with one message, that we're not a VR lab. We're really a computational imaging lab. Work on many different problems: light field displays, light field cameras, computational microscopy, time-of-flight imaging, and others. And if you're interested in that, we're going to do an open lab this Friday. If you're still around, I'd like to invite you to come by from 10 a.m. to 3 p.m. at Stanford. We're going to be demoing all the technologies that I've been talking about today live. Please email Helen Lin if you would like to come, so that she can assign you a time slot or make sure that not too many people come at the same time. So we have about 12 demos and posters. There's no talks. This is mostly a demo session. I'd like to thank my collaborators, mostly people in my group and others. And with this, I hope we have time for a few questions. I'll also be around in the coffee break.
Thank you. Hello. So, we have any questions?
Okay, so one thing I think of when I think of cyber sickness and avoiding it is just that the frame rate has to be high enough, and that's like, if you turn your head suddenly, then the display has to keep up with your motion, right? But when you talk about this adjustment of the accommodation according to how far away is what you're looking at. And that's a physical adjustment. The display moves or the lens physically adjusts. And it seems like that would necessarily be slow. That wouldn't be 60 frames per second, right? Is that a problem? Does that cause motion sickness?
Yeah, so that's a very, very good question. So latency has been one of the most challenging factors for people working on VR for the last decades. I would say with not so much LCD technology, but maybe more OLEDs and these super fast inertial measurement units, we have brought down latency to the point where it's not noticeable. And that's a huge improvement for VR. And that's where we started in 2012, maybe with the Oculus Rift. For accommodation system is much slower than most other visual systems. The response time for your accommodation system is in the order of 300 to 500 milliseconds, so half a second. It takes the eye half a second to accommodate at a different distance. So as long as you build technology that's faster than that, I think you're good. And these focus tunable lenses that we've been using run at 50 milliseconds with settling time. So that's 60 frames per second. And that's very fast and very good. Better than anything you can see. As soon as you mechanically actuate something, then you have to design something that is fast enough. The motor that we used was fast enough, but it's a big motor with lots of power. So the requirements aren't as strict as for orientation latency or other latency issues, but you have to be aware of what the response time of accommodation is.
Okay, let's take one more question.
Raise your hand high.
By the way, in the meantime, I would appreciate if you just stayed and we would do the few awards for the society.
I just wanted to ask about the problem of astigmatism. Is that significant, and how might you solve that?
Yes, that's a very good question as well. Astigmatism is something that, astigmatism and higher order aberrations for people is something that can have a significant effect. Most dominantly, the defocus is what affects people. With glasses, we can actually correct astigmatism. With other technologies, not so much. We don't address astigmatism right now. The lenses can only correct for defocus and not astigmatism. So the data I showed you were from people who we measured, the 150 participants of the study. We measured their astigmatism as well, but we only corrected for the spherical aberrations. And we got very natural responses compared to the people who already had vision correction. So it seems to be working fine, but it can be improved by correcting for astigmatism and also other higher order aberrations, like spherical aberrations in the eye.
Let's thank the speaker one more time, and thank you.